Hello students, in last lecture we have seen the basic device technology. In this lecture we will see the depletion region and depletion region capacitance. Now the PN junction is formed by introducing the third group impurity to the base, that is N-type semiconductor, and due to which there is formed some region in which the acceptor concentration is equal to donor concentration, and that location is known as PN junction. And at the PN junction, when these two regions come in contact, the holes from P region, as the holes are the majority charge carriers in P region, these holes will move from P region to N region, and due to which here the negative ions are formed at the junction in P region, and as electrons are the majority charge carriers in N region, they will move from N region to P region, and the positive ions are formed near the junction at this N region, and these negative ions and positive ions are immobile charges, and this width or this region is known as depletion region, and W be the width of this depletion region. When there is no any bias is applied or the PN junction is in equilibrium condition, this is the situation of the depletion region, and when the forward bias is applied to the PN junction, this width of depletion region is slightly decreased. As the positive potential is applied to the P region and negative potential is applied to the N region, this is known as forward bias, and when forward bias is applied to the PN junction, this width of depletion region get increased than the PN junction in equilibrium condition. And when reverse bias is applied to the PN junction, then this width of depletion region get increased. we see the PN junction in 3 different configurations. That is, this is the equilibrium condition, PN junction in equilibrium. This is the forward bias, and this is the PN junction when reverse bias is applied. Now we have to see the capacitance, that is depletion region capacitance. All of you know the capacitor, that is 2 metal plates are kept at distance d and some dielectric material is filled in between 2 metal plates. Then this configuration is known as capacitor, and the positive charges are accumulated at one of the metal plate and negative charges are accumulated at the second metal plate. Then one has to see how this phenomenon of charge storage is seen in PN junction. So there are basically 2 types of capacitances associated with a PN junction. First one is junction capacitance. Junction capacitance. And second one is diffusion capacitance. So the junction capacitance arising due to dipole in transition region, and the diffusion capacitance or charge storage capacitance is arising from lagging behind of voltage as a current changes due to charge storage effect. And as we know, in case of capacitance, the capacitance of the capacitor is calculated by C is equal to epsilon A upon D, where epsilon is the permittivity of the dielectric material, A is the cross-sectional area, and D is the spacing between 2 metal plates. So in case of PN junction, this capacitance, that is, we will see first the junction capacitance, and in case of equilibrium condition, so junction capacitance is denoted by Cj, which is equal to epsilon Si into A upon W, as W is the depletion region width, and as in case of capacitor, D is the distance between 2 metal plates. So these two can be compared, or this D is replaced by W in case of PN junction. So one has to know or one has to calculate this junction capacitance in case of PN junction when the PN junction is in equilibrium condition. Now the charge accumulated at the either side of PN junction are equal. So we may write mod of Q minus as negative ions are accumulated at this left side or towards the P region. So charge accumulated is denoted by mod of Q minus. It is equal to mod of Q plus P because these positive charges are accumulated at the N region, and as these charges accumulated at the either side are equal, we may write mod of Q minus is equal to mod of Q plus, and it is equal to Q into A into XP naught into Na, which is equal to Q into A into Xn naught into Nd, where this Q is charge, A is the cross sectional area, Xp naught is the Xp naught is penetration of space charge region, penetration of space charge region on p-type or into p-type material, into p-type material, and Xn naught is penetration of space charge region into N-type material. Na be the acceptor concentration and Nd be the donor concentration. So as we denote this equation as equation number 1, and from this equation we may write Xn naught upon Xp naught is equal to Na upon Nd. This is equation number 2. Again, as we know, this boundary or this point is minus Xp naught, and this is the Xn naught, and from this we may write W is equal to Xp naught plus Xn naught, and we will extract the value of Xn naught from this equation number 2 and put into this equation of W. We will get W is equal to Xp naught plus Na upon Nd into Xp naught. Taking Xp naught common, we will get Xp naught into 1 plus Na upon Nd or we may write Xp naught into Na plus Nd upon Nd. Or from this we may extract the value of xp naught. I will write here. Xp naught is equal to W into Nd upon Na plus Nd. So this is equation number 3. Similarly, we will extract the value of xn naught. Xn naught, it is equal to W into Na upon Na plus Nd. So this is equation number 4. Again, we know the capacitance, that is Cj, that is junction capacitance, may be evaluated by Cj is equal to epsilon Si into A upon W, and in this equation one has to know the value of W, that is depletion region width. The value of depletion region width W is given by under root twice epsilon Si upon Q into 1 upon Na plus 1 upon Nd into V naught. And by putting this value of W into the equation of Cj, we will have, as we are evaluating this junction capacitance at equilibrium condition, so in place of Cj we may write Cj naught, which is equal to epsilon Si into A upon under root twice epsilon Si upon Q into Na plus Nd upon Na Nd into V naught. As this epsilon Si may be written as under root epsilon Si into under root epsilon Si into A upon under root twice epsilon Si upon Q into Na plus Nd upon NaND into V naught. So here this epsilon SI get cancelled, and we may write this Cj naught as it is equal to A into under root Q into epsilon SI upon 2 into Na ND upon Na plus ND into 1 upon V naught. So this is next equation number 5, and this is the junction capacitance when PN junction is in equilibrium condition. Then next we will see the PN junction under forward bias. As forward bias is applied to the PN junction, the junction width get decreased than the equilibrium condition, and the junction capacitance is extracted in similar manner, that is the next PN junction under forward bias the junction capacitance is extracted under the forward bias as Cj is equal to epsilon Si into A upon W. Just the junction width get decreased in this condition, and this V naught in the formula of W is replaced by V naught minus V, where this minus V is came due to forward bias, and we may write Cj as, or first we have to write the value of W, that is junction width when PN junction is in forward bias is twice epsilon Si upon Q into 1 upon Na plus 1 upon Nd into V minus V naught, sorry, V naught minus V. Due to forward bias, this forward bias voltage is came into this formula of junction width, and from this we may extract Cj as Cj is equal to epsilon Si into A upon under root twice epsilon Si upon Q into Na plus Nd upon Na Nd into V naught minus V. So again, by solving this, we may get Cj is equal to A into under root of Q into epsilon Si by 2, sorry here, so in place of this, Cj naught may be written as A by 2 under root twice Q epsilon Si, by taking this 2 at the denominator, twice Q epsilon Si into Na Nd upon Na plus Nd into 1 upon V naught. So this is the junction capacitance for the PN junction when junction is in reverse bias, junction is in equilibrium condition, and this is the junction capacitance when the PN junction is in forward bias. So this is Na Nd upon Na plus Nd into 1 upon V naught minus V. V naught minus V. So again it may be written as A by 2 under root twice Q epsilon Si into Na Nd upon Na plus Nd and here taking 1 upon V naught common, so 1 upon V naught into bracket 1 minus V naught upon V. So in this formula, accept this 1 minus V naught upon V, the whole formula of this whole formula is for the Cj naught. So in place of this we may write Cj naught. So Cj is equal to Cj naught upon 1 minus V naught upon V raised to 1 by 2. So this is the junction capacitance when the PN junction is in forward bias. So in general we may write this junction capacitance Cj is equal to Cj naught upon 1 minus V naught by V raised to N, and N has two different values, that is N is equal to 1/2 for the step graded junction and n is equal to 1 by 3 for the linearly graded junction. So for linearly graded junction, this Cj becomes Cj naught upon 1 minus V naught by V raised to 1 by 3. So this is for the linearly graded junction, and when this n is equal to 1 half for the step graded junction. So one has to know the charge distribution of step graded junction and linearly graded junction, or difference between these two. So if we consider this as a P region and this as N region, then this is the charge distribution in step graded junction. Step graded junction. And when the charge distribution is linearly changing, then it is called linearly graded junction. So this is linearly graded junction.